Our final lecture is concerned with the elimination of toxicants and where these toxicants are excreted. Excretion of compounds is an important determinant for biological effects. Rapid elimination reduces the likelihood of toxic effects and the duration of these toxic effects. Quantitatively, elimination is reflected in the half-life and the elimination constant. The main routes of excretion are in urine via the kidneys, which is the most important route for non-volatile compounds, bile, which is often for larger compounds and metabolites, the lungs for volatile compounds, and finally, on occasion, in breast milk and in other fluids. Many compounds or metabolites are removed from the blood as it passes through the kidney. The kidney receives roughly about 25% of the cardiac output, or around 180 litres of filtrate a day. This translates into between 500 and 2,500 mils of urine, meaning that about 99% of water is reabsorbed. Excretion in the kidney involves filtration with relatively small water-soluble compounds. Large molecules are not filtered. For lipid-soluble molecules, they are reabsorbed. Filtration tends to occur primarily in the glomerulus. Active transport can occur in the proximal tubule. And finally, diffusion occurs in the distal tubule. If we look a little closer at the level of the nephron, we can see these processes annotated diagrammatically on the right. The glomerulus has large pores, and all molecules of relatively low molecular weight, that is less than around 60 kilodaltons, are filtered out of the blood. Most toxicants are filtered from the blood unless they are tightly bound to plasma proteins or in some cases incorporated into red blood cells. For such compounds, the concentration in the filtrate is going to be roughly equal to the plasma concentration of the free or unbound compound. Active transport, as we saw in the last diagram, tends to occur mostly in the proximal tubule. This often involves the active secretion of some weak electrolytes and especially weak acids. As you remember from absorption, active transport requires a transporter of some kind and a supply of energy in the form of ATP, as is illustrated in the diagram. As before, this transporter can become saturated and therefore limits their excretion. Diffusion and reabsorption can occur in the distal tubule, as we saw from the first diagram. This includes passive excretion and reabsorption of some lipid-soluble chemicals or drugs. It also means that much of the water that passes through the filtrate gets reabsorbed here. There is a concentration gradient in the direction of reabsorption. The cell membranes here are permeable, which means that it is penetrable to lipid-soluble compounds as long as the drug is in the unionized form. The next step for us to consider is what factors could influence urinary secretion or excretion. We can look at each of the different transport mechanisms separately. Firstly, filtration is influenced by things like the plasma concentration. So high plasma concentration can mean faster elimination. High fluid intake can lead to a higher rate of urine production and therefore faster elimination also. Age and disease are important factors because with the increased incidence of cardiac disease and especially lower cardiac output, it can lead to slower elimination, meaning that the compound is hanging around the body for a longer period of time. Regarding active transport, it too is affected by the plasma concentration. High plasma concentration can lead to saturation and in some cases slower relative elimination. If there is competition between toxicants and or potentially endogenous compounds, this can lead to slower elimination also. Diffusion and reabsorption are affected by the urinary pH. If the compound in the filtrate is ionized at pH of tubular fluid, it means no reabsorption. As we said, compounds need to be in the unionized form in order to be reabsorbed. An example of this would be with phenobarbital that we came across in the last lecture. Phenobarbital is a weak acid and it's ionized at alkaline pH. Giving sodium carbonate for overdose patients means an increase in the urinary pH and therefore can increase its excretion. as seen on the diagram on the right. Other factors that can affect the pH of the urine is dietary factors, such as a high protein diet. This can decrease the urinary pH and therefore increase excretion of weak bases and decrease excretion of weak acids. Some toxins and their metabolites are excreted by the liver into the bile. The liver secretes between a quarter of a litre and a litre of bile a day. Things like anions, cations, non-ionized molecules containing both polar and lipophilic groups can fall into this category. There is a typical molecular weight cutoff of around 300 Daltons. The ABC family of transporters, which we met in the first lecture on absorption, are often involved, and excretion ultimately happens in the feces. Some of the factors affecting biliary excretion include the gut microbiota, the gut microflora as they're called. These are the bacteria that reside in the small and large intestine mostly. So these bacteria in the gut may metabolize compounds into more lipophilic compounds and in some cases more toxic compounds. Increased lipophilicity can cause reabsorption in the intestine and leads to something called enterohepatic recirculation, which means an increased half-life and an increased hepatic exposure. As is shown in the diagram, we can see that normally the bile comes out of the liver into the gastrointestinal tract, into the intestine, but if it's reabsorbed, it'll pass again into the portal circulation and go back into the liver. So it's a recirculation phenomenon. Some examples for this, where there is formation of toxic compounds, include the hepatocarcinogen 2,4-dinitrotoluene. There is an initial biliary excretion of glucuronide, which is then broken down by the beta-glucuronidase enzymes found in the bacteria in the gut. The products of these reactions then get reabsorbed, causing further exposure of the liver to this hepatocarcinogen. Another example is an intestinal carcinogen, arenitessin, and the glucuronides here are broken down by the beta-glucuronidase enzymes also in the gut. The lungs are an important route of elimination for volatile and gaseous compounds and their metabolites. For example, between 50 and 60% of benzene is eliminated by just breathing out expired air. These are removed primarily by passive diffusion along a concentration gradient, so moving from an area of high concentration in the blood supply surrounding the alveoli into an area of low concentration in the alveoli sac. The gradient as shown this gradient is shown in the diagram on the right. There is a continuous gradient between the blood and the air, leading to rapid removal of the gas or the vapour from the lungs, and also rapid blood flow through the lungs aids in this process also. Finally, an alternative route of excretion is in the breast milk. This is an unusual situation because of the total fat content of the milk is quite high for nursing mothers and can be as high as 42 grams per litre. It is the main route of excretion for some lipid-soluble compounds such as DDT, chlorbenzenes, dioxins, molecules like this. For some basic compounds, the pH of breast milk, normally around 6.5, is lower than plasma and can mean it can get more readily excreted and even be concentrated in some cases. So now that we've looked at all the different methods of elimination, it's important to consider the entire process of absorption, distribution, metabolism and elimination mathematically, and we can actually quantify this. So this is a term, the disposition is a term that we can use to describe the combined processes of distribution, biotransformation and elimination. It can be described by compartmental models such as the 1-compartment, 2-compartment or even multi-compartment models, and models can be used to predict the time course of drug concentrations in the body. These compartments could represent a group of similar tissues or fluids. For example, the blood is considered a compartment, as we saw in the last lecture. Fat or adipose tissue, bone, the liver, the kidneys, and the brain are all other major compartments. As is shown in the flowchart on the right, a compound is absorbed into a central compartment, in this case the blood. It may be distributed into one or more peripheral compartments also. Finally, it can be eliminated by metabolism and excretion. As is indicated by the mathematical constants K, a compound is in rapid equilibrium with the central compartment, and distribution to peripheral compartments is reversible, as indicated by the arrows. On the other hand, elimination by metabolism and excretion is irreversible, as you might think. These compartments can be modelled mathematically depending on the model. If we consider, for example, the intravenous route, this would be considered a one-compartment model. Absorption in this case is instantaneous, as can be seen from the concentration curve on the right. The graph shows an initial high concentration that then drops quickly over time. There is also no first-pass metabolism, as it doesn't enter the portal circulation. As there is rapid distribution in one compartment, only elimination is to be considered. The exponential decline means that the rate of elimination is proportional to the concentration. This means mathematically that it is called a first-order process, and can be used therefore to predict the concentration at any given time using the equation shown in the blue box, that is Ct equals C0 multiplied by e to the power of minus the elimination constant times time, where C is the plasma concentration, T is the time, and KEL is the elimination rate constant. It gets a bit more complicated for oral administration, as absorption is not instantaneous. As can be seen from the concentration curve, the plasma concentration initially rises and then declines. At one point, absorption and elimination both occur at the same time. Initially, absorption is the predominant process, but with the rise in plasma levels, there is a rise in elimination also, which is concentration dependent. Later, however, elimination is the predominant and only process, as can be seen in the latter part of the curve, where there is almost a straight line. This can be used to determine things like the half-life, the T-half, and the elimination rate constant, KEL. Plotting the difference between the elimination curve and the actual plasma concentration gives a straight line that can be used to determine the absorption constant, or KAB. It's also important to consider that for some toxicants it might not involve a single administration and may in fact involve repeated dosing. The effects of repeated dosing will depend on the dosing interval and the plasma half-life as well of the actual chemical. If the dosing interval is shorter than T-half, there will be an accumulation of the compound in the body, as shown in the graph in the top right of the slide. If T-half is very short compared to the dosing interval, there will be a fluctuation in the plasma level, as is shown on the bottom right.